Munich and so is a bit more in the south, and we are very close to the border to the Netherlands. That's why a lot of Dutch people are working in my group because they are very good in movement science, by the way, here in Amsterdam, in Groningen, and Enschede here is around here. So this is our nearest neighbor here. Okay, something about Münster. So this is, we have a so-called Aasee. It's in Lake A. And this is exactly in the center of Münster. So this is very nice to be. If it is sun is shining, it's not always sun is shining. Mostly, it's, sometimes it's raining, as you know, Louis. And so we have 300,000 inhabitants and a bit more than 50,000 students. So the city is really, yeah, so the city life is geprägt. I don't know the English word. So it's pushed by the students, I must say. So we have an historic city center, which is very similar to Dutch cities, by the way. And yeah, we are the so-called bicycle city of Germany. So we have really a lot of bicycles. So everything what we are doing in the city is done by bicycles normally. And we have this leg side, like as I already said, and some culture. So these are the pictures from the starting homepage of our university, and I just grabbed them to give some impressions about Münster to you. This is now the start homepage of our Institute of Sports Science here in Münster. So we have some buildings. So here in that building, for example, is my group with the movement science, and there is my my office around there. This is the homepage of my group, and if you like, you can check that and see what we are doing and who we are and so on. Yeah, just as maybe some impressions about where I am at the moment here in Münster. And by the way, we have a so-called Brazilian center. And this is very nice because they are really good in trying to get some internships or money to have the cooperation between yeah, Brazil and especially Sao Paulo and Münster. So they are really pushy in this way, and it's possible to get some funding for possible collaborations. And this is what we used several times already. So Louis and I and some of the PhDs, just as maybe it's an idea for you as well. Okay, but coming back to the talk, modeling and simulation. So what are we talking about? And I would like to start with some videos. But you cannot hear the... unfortunately.
Oh, Heiko, you can, well, when you start sharing,
yeah,
you need to stop sharing. But when you click share screen, probably you're gonna see you have to click close to the bottom of the screen that is sharing with sound.
Yeah. And optimize for video clips.
Yeah,
okay.
That's it.
Yeah. Okay, I have to and try it again. Complicated way to move or to locomote. It's much easier to walk on four limbs. But if we have learned how to
ein Powerpaket sozusagen. Die Herausforderung.
Then we can also still run even if we are losing, for example, a limb. Like this Heinrich Popov, he was in our lab. This is done in our lab. And so I guess that he is running 100 meters faster than most of us, maybe all of us. Yeah? And so even though it's possible for us if we have learned how to walk, to control and to perform stable running, stable walking, even if we are losing a limb. So this is a very high coordination that we have, that we can have to show, or that we can show. The other thing is throwing, for example, throwing and catching, and we have to learn that. Here, my daughter learned it, and so this is javelin throwing and juggling. So we can learn really high skills in throwing and catching balls, and this is more or less unique. So some animals can do that as well in the animal kingdom. But how we can do it, so with how precise we can do it and the coordination that we can do for catching and throwing, this is really more or less unique in the animal kingdom. And we can ask ourselves, how do we coordinate this complex system? So how we can coordinate a huge number of different muscles. And if we try to get a better understanding about this highly complex system, we can ask, where should we start to understand that motor control? So should we start in the brain, or should we start in thinking about psychological conditions? So I want to walk or something like this. Should we better understand first the sensors, the muscles, or with what should we start? And I think it's depending on your viewpoint with what you are starting. So because movement science, I guess we should start with muscle contractions, because we think, okay, every active movement of humans, even eye blink or something like this, is based on activation of muscle. So the muscles are activated, who knows how, and generate force. And but how can muscles generate force is the next question. Here we know already a lot about the sarcomere, the muscle fibers, and the three-dimensional orientation of the muscles, muscle fibers within a muscle, and the single joint muscles or biarticular muscles, and history effects and all this stuff. What Walter Herzog will tell you a lot about that tomorrow. But this is, I think, an important step how we can start to understand motor control. But on the other hand, yeah, there's also a neural system which have to be understood. So maybe we can start in the brain, and we know, for example, that here Prochatzka made some stimulation studies in the human brain, and then from this he got that map, the homunculus, for example, and based on this we can think about how we are perceiving our body movement, our touches on the limbs, or maybe the proprioception of the movement, is that we have a large area for the hand and for the mouth and so on. And this is how we will look. We are perceiving ourselves in the body. So it's a strange homunculus that we are. Yeah, and as well, as I said already, the sensors, the reflexes that we have. So we have monosynaptic reflexes, polysynaptic reflexes, muscle spindles, Golgi tendon sensors, proprioceptors, and. So there are a lot of sensory reflex loops in the body that are necessary to control or to stabilize our movement. And there was a very nice paper with the title "How Animals Move." That's why I'm using this. It's from Bob Full, and so we know a lot about the physiology of human motor control, but we still have a lot of questions. For example, according to which criterions do we select specific movement patterns? Or are there movement primitives? Or which optimization criterion should be used, and so on. And we have a lot of theories about motor control. So for example, some of us, Mark Latache, Feldman, and so on, they say, or Bitzi, they say that motor control is a functional tuning of the resting length of a muscle. So it's the equilibrium point hypothesis, or maybe the lambda model or the alpha model. And there are several theories out there to get a better understanding how we may coordinate our limbs during walking, running. Others, for example, Auke Eisbert in Lausanne, he was publishing this paper and this very nice video here, say that it is a rhythmic coordination of pattern generators, let's say central pattern generators or spinal pattern generators. And he was simulating the salamander here, because salamander can swim and walk on land, and he was able to show that maybe the simple locomotion pattern are based on simple connections between neurons in the spinal cord, for example. And there are only some very rough information coming from the brain, but the pattern itself is maybe stored already in the spinal cord. Others, like, for example, Dagmar Sternhardt in Penn State as well. She's now in, I don't know, in the eastern part of the US, I think in Washington or so, I don't know. And she said, okay, it's a nonlinear system. So this is some ball bouncing pictures, and showing that it's when you are bouncing the ball, and this is a dynamic system. And here the dynamics of the movement or motor control is stabilizing or helping the system to get a good coordination. And together with Reinhard Blickhahn in Jena, we published or developed a more or less theory about the mechanics which are supporting motor control. So if we are thinking about motor control, we are normally starting with the central nervous system, the brain, spinal column, and then we are sending some motor commands to the muscles. And the muscles are contracting, so they are generating forces, and the forces then are acting on a limb or on a bone. And because of these muscle forces, we do get some kinematics and kinetics. And the kinetics and kinematics are interacting with our environment. So with the external environment, and this is how we are generating motor pattern, more or less. And we have sensory feedback. So maybe we are using our eyes to see our own kinematics. We have some sensors in the muscle spindles, or in Golgi tendon organs, and so on. So a huge amount of sensory feedback with delays. And this is the problem of the sensory feedback, that they are quite delayed. So we're really slow. So it takes about 100, sometimes 150 milliseconds to get the information up to the brain. So this is the typical way how we are thinking about how we can stabilize our movement. On the other hand, for example, we can also think about mechanical feedbacks. So if a muscle is, the force production of a muscle can be compared to a spring damper. So, and if there's a perturbation and you are stretching the muscle, then we are increasing the force in the muscle. And because of that, we have an increased force, which is pushing the system back to the equilibrium. So there was the idea whether it may be possible that already the very special muscular skeletal properties of humans are able to self-stabilize the movement. And we did some studies about that. I don't want to go into detail here, but this is where we can see, or we can show, that already how during evolution the muscle properties and the skeletal properties are developed in a way that it is already stabilizing our movement as well. You can see that a little bit in the next video, for example, with these passive walkers. This is just some sticks which are connected with each other. They have no actuators, and the movement pattern is only because this is an slope, an inclined slope, and therefore the complete pattern is a stable movement pattern. There are no actuators, no sensors, nothing, and it's just stable because of the special arrangement of the mechanics of that system. And this can be transferred also in some part to human locomotion. Others say that motor control is based on the reafference principle. Again, a theory, very nice experiments with your eye, but I don't want to go into deep here. And what we are doing as well is to think about motor control, especially the spinal motor control, to be a highly complex neural network, a highly recursive neural network, and we can explain a lot of things, how we can learn movement patterns, how we can recognize some movement patterns, and also the idea of this reference principle can be explained some parts of based on these recursive networks that we do have in our spinal cord. So what I want to say, I think humans are highly nonlinear, complex dynamic system. And if we try to better understand how the motor control or how this nonlinear complex dynamic system is functioning, we can do some experiments, and there are many, many very nice experiments out there, and I'm very keen sometimes how intelligent they are designing these experiments, and from this we learned already a lot. But on the other hand, we also have this kind of computational models which now can be used to better understand or maybe explain something that we already know, or maybe that we have already measured, or maybe we can explain some strange results of some experiments or something like this. So this is a possibility now. And I think during the times where we had this Commodore 64, it was not so, the possibilities that we can calculate with these computers have not been very important. But now, because of the computer technique, I think we are now able to really develop computer models of a human body and use it to maybe better understand or better explain our motor control system. This is a little bit what I would like to talk about. Yeah, computer models. Before I start talking about concrete models, I think, or I would like to discuss a little bit computer models in general. So this is a very famous drawing of Magritte, and it said, "Ceci n'est pas une pipe." So it means this is not a pipe. And what he would wanted to what he maybe wanted to say, I don't know, but what I think what he wanted to say is that this is not a real pipe. It's only a drawing of a pipe. It's a model of a pipe, but it is not a pipe. Yeah, it's only a drawing. And in the same sense, this is not a muscle. It's only a model of a muscle, where you can say, okay, it's a serial elastic element, and we have a tendon and parallel elastic elements. And this is a typical way how we are trying to model a muscle, but this is not a muscle. It's only a model of a muscle. And so we have to think about models and maybe categorize the models that we can have or that we may develop. So for example, this is a conceptual model, which is consisting of theoretical concepts and relations. So you have seen a lot of these pictures. They're saying, okay, markets. So this is a business model. Markets is influencing the customer, and the customer back the service provider, and so on. And to get a concept of relations between these things. Maybe we have this reference principle, what we have already seen, and we can try to make a model from this. So we have motor system and the plan and the muscle and the afferents and so on. And this is a conceptual theoretical model, which is used to better understand it, or maybe a model about malaria, or maybe, and I like that one, come on, this one, because this is a model, how to make a model. Yeah, I like that one. And so we can have different ways to make conceptual models about maybe human dynamic system as well. On the other hand, we have computational models. Yeah, I don't know where this is coming from, maybe some of you. So this is a computational model. And this consists of mathematical equations. For example, this is a very famous logistic equation where you can maybe describe the population development. This is now an equation, and we, depending on the parameter r, we are able to describe the time series of these data points. Sometimes we can, for example, I'm using MATLAB Simulink, and so this is a computer model, how it is programmed in MATLAB Simulink. So this is already looking like a conceptual model, but it is still a computer model with some, here, for example, we have some equations about the R model and so on. Or maybe this famous model of the Schrödinger equation about the quantum mechanics. It's also a computational model. So we can divide models that we are using in conceptual model and computational models. And when we are using this kind of models, the next step how we can categorize it is we can use a model as a black box. So these are models which are only describing the behavior. So we have an input and an output. For example, this is data that we have measured, and then we can make a regression line inside the data. And then if we have that regression line, then we can calculate or maybe predict the value depending of the input or something like this. This is a computation model, and it's only describing the behavior that we have measured. So these models are, yeah, they can describe the behavior. They are limited for the conditions under which the data have been developed. And they should be as simple as possible and as complex as necessary. For example, stock quotes can be described with these kind of models. On the other hand, we have maybe possibility to develop models which are describing the structure, the inner structure of our system. So here again, we have an input and an output, but it's not only describing the behavior. In this case, we have, for example, a real system, maybe a real neural network, or maybe this is a muscle and this is a joint and this is a bone and something like this. And so this is a real behavior. And then we can start, we have an input and an output, and then we can try to develop an excuse me for the German words here, for the an explanatory model. Yeah, so we can try to make a model about this circle, and this is describing the circle, and that one, and we can try to have the connections, and then we can start to validate the connections and so on. And these kind of models describing the structure, the inner structure of the system, they can be used to get a better understanding about the functioning of the real system. Yeah. So in these cases, if we have the possibility to develop a model like this, then the validity is not limited to conditions under which we have data, so we can extrapolate as well. And the predictions are possible. Models describing structure are able to explain the behavior, not only describe the behavior. And they should be as accurate as possible and as idealized as necessary. So this is something different. As you can see, I think it's more complicated to make this kind of describing models, but maybe we can learn a bit more of that. So examples are, for example, Apollo 13 simulation. Yeah, so this is a model, it's a real model of the real Apollo 13 simulate capsule. Or maybe trying to develop complex weather models. Here again, we try to predict the weather based on very small and interacting modules of a very complex computer model. Or maybe the Human Brain Project, which is in Europe quite famous, where they're trying to develop a computer model of the human brain. And not only as a behavior describing model, really a model describing the structure of the human brain. And we can develop something in between. So a model, a gray box model maybe, where we have an input and an output, some parts of the model can be only described by the behavior, and some parts are described in detail about the functioning of the inner structure of the parts of that model. So if we are trying to develop a model, a computer model, we have to decide, should the model, what is the, we should decide something about the goal of the model. So we have to decide the model that I would like to develop. Is it completely okay for me to develop a model which is only describing the behavior? Or would I like to get a better understanding about the structure, about an explanation of why something is X and Y? So we have to think about the goal. And if the goal is more in the area where we are trying to describe the behavior, then typically the complexity of the model is low, but the explanatory power is low as well. If we are developing maybe mixed models or models trying to describe the structure of the model, then the complexity becomes higher and higher, but also the explanatory power of these models. Yeah. So this is, but I don't want to say that models describing behavior are less important than models describing structure, because it depends why or what is the goal of your model. And based on that, you have to choose what kind of model do you have to develop. Yeah, this is, I guess, really important. Okay, computational models of human movement. So now let's talk about human movement, not only about computational models. Okay, one example that I wanted to show as very basic models are models which are developed by Reinhard Blicker and many others. So they are very basic. And for example, you know that during walking, you have that M shape ground traction force and these horizontal components of the force. And during running, you have that, yeah, more or less bell shape vertical component of the ground traction force, and again the horizontal components. And what we are typically, or what you can read in many textbooks, is that a very basic and simple model about how we can describe walking and running is the inverted pendulum model, which is describing the walking pattern to be a mass, and because of the inertia of that mass and the velocity of that mass during touchdown, and this stick here, so the inverted pendulum, then the mass is moving in this direction, and then the next leg is touching the ground and the next stick, and so on and so on. And this is how normally you will find that locomotion, walking, is described with an inverted pendulum model. On the other hand, running is described with a spring mass model, where they also say that the body, so they have a center of mass, and you have maybe a landing touchdown velocity in this direction, and then you have the leg, which is described as a spring, and because of the mass and the velocity, the spring will be contracted, and then the mass is moving in this direction, and then we have an elongation of the spring again, and then you have the flight phase and the next, and so on. So this is a very simple way how biomechanics scientists have developed a simple model, as simple as possible. They are really famous, and they try to describe human locomotion, walking and running. But there is a big problem with this model, because we have two problems with this kind of models. The first one is, if you try to model or to calculate or to describe human walking with an inverted pendulum, you can try it on your own, but with computer models, or maybe with a stick which you are throwing onto a ground traction force plate, you will never get an M-shaped vertical force. Yeah, this is not possible with an inverted pendulum. So why should we use an inverted pendulum model to describe walking, even if we know that the vertical ground correction forces that we are measuring are completely different? For running, it's really okay. If you're using a spring mass model, you will get this kind of vertical ground direction force. This is one problem. The second problem is, if you are walking and increasing your walking velocity, suddenly you will start to have a transition between walking and running. And how can you describe this transition? So it's then suddenly a stick changing to be a spring or something like this. So we cannot explain that as well. All these studies have been done by Hartmut Geier. He was in Jena as well with Reinhard Blickhahn. And he made then the assumption that maybe walking can be explained as well, not with a stick figure, with an inverted pendulum model, but why don't we also describe walking only based on two springs? So this is the left leg and the right leg, and then we have a double support phase and a single support phase. During the double supports, there's two springs on the ground and so on. And if we are using this model, it's again still a very simple model. We are able to not only describe now the walking pattern as well with the same model, it's still a spring mass model, but also the transition between walking and running is easily described with this model. And the calculated ground traction forces are very nicely these M-shaped forces. So I really like this example, even though that I haven't done this study, but I really like it because it shows that if we are trying to develop computer models about locomotion, we can explain really a lot of things based on these simple models, but we have to do it in the right way. Yeah. So it's an easy way to describe walking and running. It's a spring mass with two springs, and then we can describe we can calculate long jump and running and sprinting and all this stuff. So it's a really powerful model, and it's easy to calculate. You can do it nearly in Excel and don't need complex computer programs. So this is just an idea how we can use computer models to get a better understanding of human locomotion. Now I would like to switch to another way how we can use computational models. And this is what we have done here in Münster during the last years. So the question is the following. If, for example, we have this typical situation that Superman is landing on the street. Everybody knows that situation, and maybe you can ask, because Superman do have some problems with knee pain, and then Superman goes to the medical doctor and say, I have knee pain. And then the medical doctor is saying, this is because the forces during your landings are much too high for your knee joint. And then you start the treatment, and yeah. But the problem is, how do the medical doctor know which forces are acting in the knee joint of the Superman? Because we are not able to measure these forces. So, for example, or if I'm walking down the stairs to the kitchen, for example, and I ask myself which forces are acting in my knee joint or in my hip joint, it's impossible to get that information because I have to place a force transducer into my knee joint, and this is a surgery, and it will hurt and so on. So how can we get that information? So by experiments or by measurements, it's nearly impossible. I know that there are some situations where they have measured already something and the Achilles tendon and with something, but normally it's not possible. And therefore, I think maybe we can use computer models to get that information. So why are these computer models necessary? I would like to explain that based on this example here. So if, for example, I would like to know which forces in the elbow joint are while I'm holding this external mass. Yeah? So there's a mass, let's say, of 10 kilogram. And if I ask you which forces are acting here in the elbow, you will say, okay, this is 10 kilograms, and we have the gravitational acceleration. So this is minus 100 Newton. And because let's assume that the hand and the elbow, the lower arm is massless, but then you have 10 kilograms and you have 100 Newton, which is pulling on your elbow here in this direction. But this is not true. This is the result that we will get if we only look onto this situation from the external viewpoint. So this is the external mass, and here's the external force. But we have a lever arm here. And because of the lever arm, the lower arm will move in this direction. But if I'm holding the hand in this, or the arm in this position, there must be an inner muscle force which is counteracting this external torque. Because the lever arm is much lower for the muscle compared to the external mass, let's say it's 1 to 5, then we need to generate 500 newtons with the muscle to hold the external 100 Newton of the mass. So there is an additional force generated by the muscle in this direction. And if we sum them up, maybe we get something like 500 Newtons in this direction. So if we will measure the force in the elbow joint, the result would be plus 400 Newtons because of the inner muscle forces, and not minus 100 Newton that we could assume based on an external view on that situation. So if we don't have the information about the muscle forces that are generated in our in our body, we have no chance to say something about the forces in joints. So we can say something about the external torques or moments, but we cannot say something about the inner muscle forces. And here, maybe computer models may help. So because of that, we have developed a computer program which is quite, which is called Myonardo. We have made it on our own. It's programmed in MATLAB, Simulink, and it can be compared to OpenSim, and we can do some. So we have described the human body with 35 bones and joints and a lot of muscles in that body. So we have more than nearly 700 already muscle line of actions in that model. Each muscle is described with the force length and force velocity. So with a Hill type muscle, we can do this called expanded inverse dynamics. So we can calculate the torques, as I showed in the elbow example, but we have also some possibilities with different goal functions to estimate the muscle activation for each instant of time. And we can also predict the ground reaction forces. I will show you some pictures for that. And the forces in each joint, mixed dynamics. So we can say that some parts of the body is driven by measured kinematics, and maybe some limbs are simulated while forward simulation. So if with an activation of the muscles, and then based on the muscle forces, we can predict the movements. We have different possibilities to measure the movement. For example, we have imports for Qualisys X and Simi, Viken, and even more already. And at the end, we are using a virtual reality. I will show you that later on, to present the results of our calculations. So this is the front end. We can choose which joints should be analyzed. So in this case, all joints are active, and we can say, okay, I'm only focusing on the right knee, and then we can turn off all the other joints, and then the calculation time is much faster. We can read here the T-pose and some movements, and and we have also possibilities to change the solver and step size and all this stuff in behind. But this is more or less general way how we can make these calculations. And then you push the run button, and then it's starting to calculate. The result of the calculation is, for example, to get a visual impression of that, is something like this. So here you can see from the front and from the back side, you can see all the muscles which are included in the model as blue lines. And this is an older way how we can simulate it. So if the muscle is active, it becomes a bit thicker and the different color. And this is a way how Bob Biomechanics is another computer program is doing it as well. So we have a collaboration with him and we were able to use that one. So this is a running simulation. So here you can see based on the colors which muscle is active and generating which force depending on the color. And this was done by, so the muscle information is only calculated. So it's not measured based on EMGs or something, it's completely calculated. This is a subject which was running over some force plates in our lab. And based on that, we make these calculations. So because now it seems that we have the possibility to get some knowledge about all the muscle forces during a movement that we are performing. And only if we know which muscle is generating which force during an instant of time, we are able to also predict or to calculate which forces are acting in the joints. And we named that computer myography. And the idea is that for medical doctors, this is just in comparison now. So for medical doctors, they started with some X-ray systems, so where we have a view into the body, but it's one picture through the complete bone. And then you can see maybe a crack or something here, and if there's a fracture or something like this. Then they developed the computer tomography, where you have slices of that bony structures, which is much more detailed. And at the end, now the MRI, where you have also information about the muscles and soft tissue. If we are trying to analyze human movement, typically we are using functional movement screen, and physiotherapists or sports trainers or something are able to inspect these movements and say, okay, you have a problem with the range of motion in the right knee compared to the left knee and so on. This maybe can be compared to the X-ray situation. This is a more integral view on the body. What we think maybe computer myography, so the possibility to calculate at any instant of time which muscles are acting which forces, may be compared to the computer tomography. Because you get slices during the function of a human movement. And the next step is, which is already here published by Gaia, is if you know already which muscle is generating which force in which direction, and you also have the information about the forces in the joint, then you can also calculate the stress and strain in the bone. So this may be named then computer myo-osteography. So the result of that could be, for example, this is an example of what we have calculated. So this is a deep squat and a drop jump. These are the phases that are analyzed, the yellow boxes here. So this is the deep squat, the right and the left knee joint and the ankle joint. And then we can calculate, and red is left and blue is right. And then we can calculate the asymmetry of that movement. And it looks to be quite okay. So we have an asymmetry of 7%, or here 9 or 6%. But if we are calculating the forces in the body, then the asymmetry is much higher. For example, -10 or -16 or -19%, because the forces that are generated in the joints of the body are not only depending on the angle itself, it's depending on your weight shift, on the velocity with which you are doing the movement, and therefore the story about the forces in the joint can be completely different compared to the story about the external movement performance. And yeah, but it's at the moment it's only possible to expect the external viewpoint. Another example that we have calculated is here from the field of badminton. So in badminton, you do typically these lunge movements. So on the left-hand side, you will see now a movement with a technique where the trainers say it's a good technique and the right one is a bad technique. And I think you will see that it's really hard to see what is the difference between the two techniques. Yeah, so this is the good way how the subject did it, and this is now the bad way how she did it. The difference is, maybe some of you know that or saw that, is that during this lunge movement, the trainers say that the tip of the knee should be above the tip of the foot. And here in this case, you can see that the tip of the knee is before the tip of the foot. And then you can say, okay, yes, it's in centimeter or two. What is the problem with these two different techniques? And the problem is, if you are calculating the forces in the knee joint, and this is what we did here, is that you can see that the mean force here is about roughly 4,000 newtons, newtons in the knee joint. And in this case, it is above or about 4,500 newtons. So it's more than 10% more. And badminton players do that more than 200 times in a game and during training and so on. And if you are able to decrease the joint forces by 10% by changing these techniques, this is a huge improvement for prevention of these sportsmen or women. We have used that as well, for example, in the field of ergonomy. So you can see here now a subject standing on our force plates, and we have kinematics measured with the equalizer system, lifting a box, and then you can calculate for the whole body which muscles are active. We have this kind of virtual reality. So this is a hurdle step, and then now you can see, for example, nicely how the psoas muscle is active during this movement. A muscle which is typically not be able to measure, we cannot measure because it's a very deep muscle. We have a visual report. So for example, here now, this is a Y balance test. And then you can choose which muscle should be presented here in the analytics, or maybe you can choose also which joint. Let's say we take now the knee joint, and not the right joint, but the left knee joint, and maybe the rotation around the y-axis, and then you can plot that, and you can show with a bar that, wait a second, with the slider, where you are here during the movement, and you can directly see which forces are there. Okay, then the question is what we are calculating, is it valid? This is the last few slides that I have. It's about the validity. So is it true what we are calculating? Is it representing the reality? And therefore it's necessary, always necessary, this is an ongoing process. You cannot stop with it, because it's always a very big and important thing to validate your model, even if you're using this kind of complex models. So here you can see the force-length relationship and the force-velocity relationship of muscles. The dotted lines here are different measured values for single muscles mostly, and for the force-velocity as well. The black lines, and this is the passive line here, is how OpenSim is modeling the force-length relation and the force-velocity relation, and the red line is how it is represented in our model. Yeah, so with this, we are trying to prove or to show that maybe how we are describing the muscular force production is valid. We can discuss a lot about validity, but maybe this is a possibility to say this is more or less valid. Another possibility to validate the model is maybe to use some interesting experimental data. So as I said at the beginning, it's not possible to calculate or to measure the forces in a knee. But this is not true in general. For example, here you can see a subject, a patient, and he got an knee prosthesis in the left knee. And it is done in the so-called CAMS knee study from the Charité in Berlin and from the, what is it called in Switzerland, the later on. But this is very important CAMS knee study, and the important or the specialty was that the prosthesis of the knee joint is an instrumented prosthesis. And you can see that in that next video. On that video. So this is, stop here. So this is the prosthesis, and they placed a force transducer here on the tip of the tibia plateau. And so they were able to measure the forces in the knee joint while the subject is doing these movements later on. So they measured the kinematics, the ground direction forces, and the forces in the knee and some EMGs. And I got the data set, it's 6 patients. And the first thing that you can nicely see in this experiment here is that even though that the ground direction forces, so the forces below, let's say the left knee, is about 400 newtons, the measured forces in the body on that tibia plateau is about 2,500 newtons. Yeah. So where is this force coming from? It is because of the muscles of the knee extensor muscles of that subject, of that patient. Yeah. And we use that information to try to validate our model. So this is now a prediction for squatting movement, as you saw, and walking as well. So they have also measured some walking data. Black line is the mean of that CAMS knee study, mean value of 6 subjects and the standard deviation. And the red line is our prediction. And these are here the horizontal forces in the knee joint and here as well. So it is a quite, in our mind, a quite nice correlation between the prediction and the measured values. And here, as you can see, it's about 2 to 2.5 times body weight. So it is in the area of 2,000 and 2,500 newtons. I have 1, 2, 3, 4, 5 slides left to let you know. So this is now a situation, for example, soccer player in a gym, and he's wearing a so-called X-Sense suit. And based on that, you can measure the kinematics of that subject without cameras, and because of these IMUs which are in that suit, and based on this we can get the kinematics. But what you can imagine, we have no possibilities to measure the ground direction force in that complete gym. So we only have the kinematics but not the ground direction forces. But if you think about, if you're standing on a force plate or something, and you know that your body mass is about 100 kilogram, then you can already predict that you will measure about 1,000 newtons with the ground direction force plate. So if we know the mass or the mass distribution, and we also know the acceleration of all these segments of the body, it should be possible, and as you can see in this slide here, it is possible to kind of predict already the ground direction forces based on the kinematics and the computational model. So here you can see the measured and predicted ground direction forces from the Myonardo. So this is the vertical force. Maybe you don't see it very good, but this is the thick line and the thin line, and it's quite the same. And the first one is the measured one, and the second line is the prediction only based on the kinematics. And this is only here for the horizontal forces. As you can see here, there are some deviations here, but the description is quite okay. Even though that we, for example, if we don't have the possibility to measure ground direction forces, we now have maybe a possibility to estimate them in a way. Or maybe during running, this is a jogging velocity, and here again you can see right foot, left foot, again the prediction of the two models. So it seems to be possible, or it is possible already, not only with Myonardo program. This is also, anybody is another computer program which can already predict that, and OpenSim, I guess, can do that as well. So, but it's possible based on the kinematics and a detailed model of human body to predict that. And then, for example, we can calculate the forces of the mustus intermedius during running for the left and right leg. And I have chosen this muscle because with an EMG, it's not possible to get any information about the vastus intermedius because it's a very deep muscle again. Okay, so ceci n'est pas un pipe. Still, what we are developing, all the computer models, if it's a stick figure or a spring mass model or complex model, or maybe just a regression line or something, it's only a model of the reality. And this is what we always have to have in mind. And I would like to finish with the next slide, as this was not a real lecture, it was just virtual. Hope to see you maybe soon in reality in Sao Paulo or maybe in Münster. And it was a pleasure for me to give a talk to you all. Thank you very much.
Thank you, Heiko. Thank you for this very nice presentation. I think students, they have, well, I think that your presentation was very in line with the other ones we had before. And I think you have a lot of questions. Heiko, well, the first question we have here was someone from YouTube. So I'm gonna read, but for the other questions, I will ask to the students to make the question by themselves. Then we can turn it more active conversation. So Bill Walker, Exapod, ask you if you have any comment about the whole of passive dynamics and active control in dynamic human manipulation, for example, juggling. How do they access each other? Is there a final motor output they're waiting, that weighted sum?
Yeah, this is a very nice question, and I like it a lot because this is when we developed the idea of self-stability during the phase when all these passive walkers have been developed, we have been able to show that a lot dynamics can already be stabilized and explained only by the passive dynamics. And but if you look into detail, for example, for the spinal column, yeah, we have also did some simulations for that. And if you do some experiments, you can see based on the experiments that the pure mechanical stabilization, passive mechanical stabilization, is not enough to stabilize the upper trunk, for example. So there, for example, you need to have reflexive motor control stabilization of the spine. There's a very important measurement of Punjabi, for example, who showed that only 9 kilograms can be stabilized by an spinal lumbar spine, where all the muscles are dissected. So I think to get a stable movement, you need to have this neural motor control stabilization. But as you can turn your question in a maybe vice versa. So how stupid would it be if the purely mechanical system will be developed via evolution to be unstable? This would be the different viewpoint. And then it would be much more complicated to learn movements like walking pattern, or and therefore the burden for the neural stabilization system and the motor control system which be much higher. So this is what I would like to answer. So I think it is a very intelligent, no, I don't want to use that word. So during evolution, there was a system developed which already brings up some kind of stability or supports the stability, and then additionally we have this motor control system which is then necessary to perform this very nice movement that we can.
Okay. Thank you, Heiko. Lydia?
Yes. Sorry, I'm out of video. Thank you very much, Professor, for the lecture. I learned a lot. I just have a think. Do you think it's possible to use computer modeling to help clinical decisions? For example, runner with frequent pubalgia. If we get the kinematic and kinetic data of running, would it be possible to understand better the imbalance between the muscles, the adductor and abdominal muscles at the pubis? Do you think it's possible? And how far is it from our reality? And I don't know if I missed something during the lecture, but can we have access of the Myonardo? How is the system? Is an open project, or is this? I just want to know a little bit more about it. Thank you very much.
Yeah, thank you for this very nice question as well. And yeah, I think it is, and I think especially in the future, it will be normal that we are using this kind of techniques to support the diagnosis of medical doctors or physiotherapists. I think this will be the future, especially when the kinematics, the possibilities to measure kinematics will become more easy. If you think about open pose, for example, maybe you know about that you only use one, let's say from your mobile phone, a video, and then from that you get already some kinematics, and this will develop a lot in the future. So I be very sure that in only a few years it is much easier to measure kinematics in a very accurate way, and the computer programs becomes more and more powerful. And so I think it will become a method that's used for medical doctors. And I say that, by the way, we have just started a startup here in Münster with that Myonardo program. It's called Predimo, predimo.com. And based on that, at the moment, we are just developing this kind of possibilities to support maybe in future also medical decisions. Yeah, this is what we are trying to develop at the moment. This is part of the company. To your question about can you use and get that program? This is so we have. It is possible for science. So if you apply for that and then you have to sign a contract that you only have to use that, you are allowed to use that for scientific purposes and so on, and then we can make a collaboration, and then you can have the possibility to use that program as well. But at the moment, because we are a startup, we are discussing what's the best way to develop that. But again, if you are interested in doing some projects or using the program, just write me an email, and then we can try to arrange something in this direction.
Okay, thank you very much.
Yeah, thank you for the question.
Ricardo, thank you, Lydia. Ricardo?
Okay, can you hear me?
Hmm?
Okay, thank you, Professor, for the presentation. And my question is about the virtual reality and technology that you use in Myonardo. When you show for us that this technology is used for people see the own body, my first idea is about embodied cognition, because it's very common to use in this approach the body perception. And my question is, if you do you use an embodied approach or illusion in participants immersed in virtual reality in their avatars?
So we are using at the moment Unity, as the programming language to develop these virtual reality stuff. I think it's not only presenting some colored pictures and to impress people to do this virtual reality development. But if, for example, an athlete or maybe a patient do something, a movement in a wrong way, it is always a big problem for the trainers or physiotherapists or medical doctors to explain to the subjects what they are doing in a wrong way and how they should maybe change their movement. And to do that, it's important, really important, that you present the measured data not only as a graph or something. You have to present it in a virtual reality in 3D, maybe also in a reality which is close to where you are at the moment in, maybe in the lab or in the gym. And we are also developing some possibilities to even use photogrammetry, it's called, to take a picture, a photo of the face and to project it on the 3D avatar, because it's important that you are trying to believe that what you see there is your movement and you have to change something. And this is why we are trying to develop these 3D models. And I think we haven't done some studies about that yet, so maybe this could be an interesting collaboration because we cannot do everything. But we strongly believe that this is important, especially for treatment or something with patients. I hope this was a bit of an answer to your question.
I think yes. Thank you.
Thank you.
Professor, can I do a question?
Yeah, please. I don't know who was
okay.
Professor Lewis.
Okay. No, okay. I think you don't need to change. You need to add more things. I have the same difficulty. I am an engineering, but my passion was physical education. So I quit my very well succeeded career in engineering to do physical education. And in the gym, I have this difficulty. How can I explain to my students the differences in the movement? And I will show you something less sophisticated for you, but so you understand my points and see. Let's see if I can move the camera here.
Yeah.
Let's see. I don't know. Hold on. Here is a picture of 3 persons doing a handstand. I don't know if you can see.
Yeah, I can see, yeah.
Okay, you see the 3 individuals are doing the handstands and all of them are in the equilibrium. However, each of them are completely different. If you think about the bones, the structure, I didn't do the computer, but I did this manually, like say, thinking about bones, joints, you cannot compare each other. But so I think your Myonardo is very well. The complexity is that in the Earth now we have maybe 6 billion Myonards. That is what I'm trying to say to you. So maybe you do not need to change, but maybe the researcher or the doctor need to look for you and try to understand your situation. I don't know if I'm clear to what I'm saying, because for instance, looking to these 3 students doing the handstand, each of them are in the equilibrium, respecting their own limitations. If I try to take the middle guy and maybe try to do like in the lady position that seems to be doing with less energy and less effort, maybe the guy will fall and have a break harder than the girl, because the mass and the current distribution of him is not properly developed to perform the movement the same way the lady. This is some questions I have. Maybe I would like to have your opinion on this. But I think when you are talking purely about mechanics, I like this because mechanics explain a lot of things, and all the variables you add, I think they are excellent. The difficult is the variability that we find in the real life. That is the challenge.
I think I can sign every sentence that you have said. Absolutely. It's a huge effort that we are trying to do to individualize our model. So the first, there are several steps. Maybe I don't have the slide prepared, but we made several steps to develop a model which is more individual. So the first step is, if for example, we first measure a T-pose of the subjects. Based on the T-pose, we get the individual segment lengths of the subject. So this is the first step of individualization. Then one very important thing is that we are measuring the outcome. For example, the three pictures that you have shown, we can measure that. Yeah, and then based on the kinematics, we then get completely different torques and forces in the joints. Yeah, and just 2 weeks ago or so, we have finished that we have included a lumbar spine with the 5 lumbar segments and the cervical spine as well, which is included with all the lower muscles and so on. And last answer, maybe we can have a collaboration here as well, because Charlotte Lemuel and Rosemarie de Graaf from our group, they are doing experiments with how subjects or people are learning handstand walking. Yeah, and this is what I was starting to smile when I saw your pictures, that we just made these experiments, and we have a ground traction forces and 3D kinematics and some EMGs as well during handstand walking. And unfortunately, because of Corona, we only have a few subjects now. I think it's 1 or 2, but yeah, we are trying to do these experiments, and maybe this would be a nice possibility.
No, I have several. I am engaged on this also with pilots, race pilots from Mercedes-Benz Challenge. So I think, and they have several questions. I have more questions than answers, but I think you are million times more advanced than myself, that I still in the sketches. So that's why I'm very interested in the collaboration.
Yeah, nice. Thank you very much.
Okay, you are welcome.
So Professor Lewis have to repair the roof, I guess.
I might.
Vinicius.
He was the one, Professor Luis was the one that stimulated myself. If I am in the course, the physical education, also it's part of him.
Vinicius, sua vez.
Hi, Professor. Thanks for the great presentation. I would like to know that in the middle of the presentation, you showed us a model of ground reaction forces during walking and during running. And I would like to know if you believe that arm swing can somehow influence these ground reaction forces during walking and during running.
Can you repeat the last sentence again? Because I didn't got that.
I'm sorry, my audio, I think it's a little bit low. Do you believe that arm swing can influence the ground reaction forces during walking?
Yeah, absolutely. So the arm swing will change the boundary conditions for the legs, and based on that you have a change of the kinematics, and based on that you have a change of the ground reaction force that you will measure. I'm quite sure about that.
Okay, so you believe that an increased arms to knee would increase ground reaction forces and the opposite the same?
So, for example, if I have problems to understand your audio, but I hope to can give an answer to maybe your question. I see that this spring mass model is not able to describe arm swing because it's just a point mass which is describing the complete body. But the principal the principal shape of the ground traction forces can be easily or nicely explained by that. And then the nice thing is as well, if you, for example, measure ground traction forces with and without arm swing, and then you have a difference in the measured ground traction forces, and maybe based on the simple spring mass model, you can see what part of the measured ground traction forces is now influenced by the arm swing, for example. No? So even though that you don't have the arm swing in your model, it could be possible to use it as an explanation what part of your measured forces is changed here, for example. I hope this is maybe a bit of an answer to your question. Or maybe.
Well, of course. This is very good. Thank you, Professor.
Thank you very much.
Okay. Monique.
Hi, Professor. Thank you for your presentation. I have questions about the method. For example, how did you record the knee joint bonds? Is it possible to record the scapula during the movement? If I know the muscle activity and the scapular kinematics, can I know about the scapular muscle first?
So this is again a very good question, as all the questions are. So typically I will ask you, for example, for the knee joint, first coming from the knee joint, and then I come back to your question again. So if I ask you, what is the flexion angle of the knee joint? And then you have several possibilities. So for example, you can place some markers on the skin and try to calculate an angle between these markers, maybe on several parts of the limbs, on the femur and the tibia, and then you can get an angle. But is that now the angle of the knee joint? It's just an angle between some markers on the skin. If you say I have the bones in the hand, for example, and move them, even though it's difficult to define what is the real angle of the knee joint. And you always have to do some definitions and say then this is not the angle. And now for the scapula, so the scapula is part of our model. So the structure, so the segment is in the model, but to be honest, it's just fixed to the trunk. Because at the moment in Münster, we don't have good possibilities to really measure the scapular movement. I know that there are some papers, I think from the group in Amsterdam or Groningen, I guess, they have made some nice measurements of scapular movement. And based on that, so if it's possible to measure or to get some information about how the scapula is really moving relative to the trunk, then we have some muscles which are attaching to the scapula and the trunk, for example. And then if you have the movement during the kinematics, then it would be possible to get some information about the muscles. So you can get maybe the information how the muscles are changing the length and the velocity during the movement. And if you are able to calculate the torque between the scapula and the thorax, and this is again a quite complicated part, then you would be able to calculate also which forces the muscle have to generate this torque. Yeah, and these are quite complicated steps. So at the moment, I must admit that the scapula thorax movement is just fixed at the moment. So, but there is a so-called Ghent shoulder model, also ENTH or something like this. It's in Dutch city, Ghent or Gent shoulder model, and this is a quite advanced way to describe the shoulder movement, not only the scapula but also the clavicular and the humerus and so. And I think this is more advanced than our model is at the moment.
Okay, thank you, Professor.
Thank you, Monique. Now, Michaeli.
Hi, Professor. Excellent presentation. Thanks. I would like to know a little more about the validation between muscles modeling and simulation, and what was measured by electromyography.
So we did some experiments in our lab as well. So we have some EMGs and the kinematics, and students during doing this kind of measurements, and then we are comparing the pattern of the activation which are predicted by the Myonardo and the measured EMG values. Or for example, for the CAF5006 study, at the moment I'm nearly finished to write a paper about that, and I can send you then the manuscript. And they have also measured for this CAF5006 study, where they have with these patients with the prosthesis, they have measured I guess 16 leg muscles, so we have compared the predicted activation of our muscles with these measured EMG values. I do this kind of validation, but I know that it is not a real validation, because the step from a voltage that you are measuring at the skin to the activation of the muscle in the body is quite large. So there is, maybe we can compare the pattern and see there is, maybe the pattern is quite similar. You can calculate also some cross correlation statistics or something like this, but at the end it's only an inspection, yeah, because we have not the real information about, we cannot measure the activation of that muscle during movement. It's only an indirect validation, I must admit. But this is one of the biggest problems that we have for this modeling stuff. So we can calculate it, but we have really problems to get good experiments to really prove that the calculated activations, or maybe the calculated forces, are the same or identical to the real activation of forces in the muscles. This is a problem. It's always an visual inspection.
Yes, I analyze this. We use computer muscles modeling in the OpenSim, and it's a big challenge. But thanks, Professor.
Yeah, we can, if you like, we can talk about this or discuss it via email if you like, and try to share our experiences.
Yes, thanks.
Thank you, Michaeli. Now, Franklin.
Hi, Professor. Thank you for your presentation. My question is, considering the limitations of numerical integration methods, what is the best way to minimize the problem of impact in landing or running simulation?
At the moment, we try to just neglect that phase of impact. Okay. I think we have to, so we have, so with our methods, we are able to measure the kinematics with up to 500 Hertz. Yeah, so typically we are using 250 Hertz or 200 Hertz. This is one step. Then we are using typically an ODE 5 solver, and we can change the internal step size up to, so we are using typically the measured step size if possible. And we use some kind of an filtering, and for walking and normal running, we are using this about 20 Hertz Butterworth filter. And if you're using these filters, then you are able to calculate the integral result of it. But I think there are some limitations. If you really would like to analyze the impact behavior, this is during milliseconds.
Yes.
And then I must say, okay, there we are at the boundaries of what we can measure with the kinematics, and also in the boundaries what we can really predict, and you are you yourself be confident with your results. So you can calculate something, but to see whether this is really this is the reality during the impact, this is quite hard, I must say. And I think at the moment don't think that I will or would analyze these impact situations with our model. Maybe there are other models on the market. Maybe OpenSim is better in this area. But at the moment it's not. So we are just developing, maybe this could be a step in this direction. With Rosemarie Dubbeldam, we are developing a more sophisticated foot model. This foot model is based on 6 segments with springs. And then we have, during this mixed dynamic approach, that we have the measured kinematics, let's say, of the lower limb, and some part of the foot, but then during the impact, the movement of the segments of the foot can be simulated in a forward dynamic approach. Yeah, and this could be maybe in future a possibility to get some information about the interaction during this impact situation, because then you have a rough movement of the limb, and you can use a very in a forward dynamic simulation of the movement of the foot with the model. So this could maybe a possibility, but at the moment we haven't done that.
Nice. Thank you for your.
Thank you for the question. But I think you know the stuff of these wobbling mass models, no? And
yes.
I think they are quite, with Benno Nick and Gruber and Günther, they have done some nice studies about this, how these wobbling mass are influencing the impact situation. If you have, I know that some of them and some paper of them, and if I can give you some information, just ask me.
No.
I don't know.
Yeah. No, thanks. You clarify. Thank you.
Thank you.
Thank you, Franklin. Now, Adri.
Hello. Thank you. Thank you for your excellent presentation. And I saw on the Myonardo that it's possible to upload Xsense system data. And then I wonder if the biomechanical modeling present the same variability in kinematic data get from IMU than kinematic data get from traditional motion analysis systems.
Yeah, we just made a very huge experiment for that. So we have an Xsense system in the lab and the Qualisys system, and so we have, I guess it was 15 subjects wearing an Xsense suit and with the kinematics marker of the Qualisys system simultaneously. And then they did some, I think it was 10 or 12 different movement times on our force plates. So we are very lucky that we have 8 large force plates in our lab, such that we can measure, let's say, jumping and sprinting and cutting movements and other stuff. So we have ground traction force, we have the kinematics from Qualisys and the kinematics from Xsense simultaneously. And at the moment, some students are making this labeling for the Qualisys stuff, and the next step is now to do the calculation with the 2 different methods with the Myonardo to see how the values of the forces and so on are changing depending on the different measuring devices, even though that it was exactly the same movement. Yeah, and the next step is then that we will also predict the ground reaction forces with the two systems and see how the prediction is different compared to the measured ground reaction forces. But this is what we are really at the moment analyzing.
Thank you.
And what I can already say is that for the, I think it was a cutting movement where the subject is running to the force plates. On the force plate, they are going to the right. And there it seems that also for the equalizer system, the predicted ground reaction forces were really nice. It was one subject which I just looked at. And for the X-hand system, but we have to redo the analysis, it seems that there are many of the peaks that we are measuring are neglected because of the filter and of the reduced frequency that we have. So our X-hands can measure, I think, 240 hertz or so, but even though seems to be some Kalman filtering and so on in the system, and based on that, the peaks are filtered away. This is at the moment my impression, but we have to wait until all the data is analyzed.
Thank you.
Yeah, thank you.
Professor, I have a question, if I may.
Yeah, oh, sure. Go on.
Well, firstly, thank you for the presentation. That was very interesting, and I have a perhaps naive or overly hopeful question. I was wondering whether those simulations, they have been used, for instance, to guide the development in youth athletes during complex movements, perhaps in terms of how to better define some sort of performance training and so on, or if failing that, perhaps to avoid types of motion that might lead to injury later on. So what would be the experience in Münster about that?
The experience is in this kind of clinical stuff really low. So we haven't done this kind of studies, and so I cannot say something about experiences here, how this is supporting therapy or maybe training or motor control, and especially in developing children. This is so the only thing that I can say is that we made a comparison study where we still have to wait because of the corona of the control group. So we started the measurement, but then we have to stop it. And we measured some children with and without ADHD. And the children were between 8 to 10, 11, 7 to 10 years old, I guess. And we measured already about 30 or 35 children with ADHD in our lab. So they have to make some balancing tasks and some goal jumps, the right word. So they have to jump directly to a line, which is a meter away or so. No? And some balancing on one leg, and to get some information about their motor control ability. And at the moment, we are analyzing the torques in all the joints during balancing on beams that we have to do. And some years ago, we made a study to show that if it becomes more complicated to balance because the beam size is reduced, that the motor control that you are using is changing from an ankle-hip strategy to an upper body strategy, something like this. And then after the first measurement, the subjects or the children got a training, let's say, in skateboarding. So in Münster, we have Titus Dittmann, they have so that they can make some skateboarding in a skater's gym. And after 12 weeks, they came back and we made a remeasurement. And there we were now able to show that for example, the jerk of the ground traction forces seems to be a bit smoother for this ADHD 3D children after the skateboarding intervention, and we got also some psychological parameters like how self-confident they are and something like this, and this improved a lot, also much better than the motor control that we have measured. But to publish that, we need to have the control group, and the control group we cannot do at the moment because of Corona. It seems that maybe in May we can start again with these kind of measurements, and then we try to publish that. But this is the only way that we did. So I must say this is nearly no experience that I have with this kind of question that you have.
And maybe in your experience and let's say speculation, would you think it's feasible to use the simulation to guide training when the difference is smaller? Let's say if we're thinking about a youth athlete that might reach college level sort of performance to those athletes who will develop and become a world-class athlete. So I would imagine that if you look at the movements developing, they will have some difference, but they will be small. And to my mind, the earlier we can, let's say, detect those differences and then try to enhance them, which now we would rely more and more on the trainer and the athletes. And do you think it's feasible to get this computational help on that?
Yeah, also I don't think that we are able to measure a children and predict whether he or she will become a world champion or so. This is not possible, I think. But what we can do, we can measure the actual status of the children, and we can try to predict what is the most effective change for the next learning step. I guess this could be possible. Yeah, and the nice thing here is, I guess, that I was showing the results of Qualisys and Xsense, but there are also these very nice new methods where we can have a markerless movement analysis in 3D. Yeah, like for example, the company of TEA from Canada, or Capture in Germany and Simi in Germany. These companies are able, or maybe also this Open Pose project, which is very nice, where you can where you don't have to place any markers. And I think this is necessary if you would like to measure a group of children doing the movement, and based on the shape detection, you are able to get the kinematics in a more and more accurate way. I think at the moment we are at the border, we can really say that this is really, maybe it's already better than marker-based measurements that we get. And then you can use the kinematics, use it, input it into our Myonardo, and it's so we are just, as I said, in this company that we are working already together with hospitals and with football in the Premier League in Germany, with some teams, and also with a team in the NBA. And so it seems that these methods they are just starting at the moment. I think we are at the edge that we can and we will use these techniques normally in the gym, because it's much easier to use than it was in the history in the last years. And therefore I think this will be part of normal what is it called, Leistungszentrum, normal centers where you try to support young athletes to become world class. I think this will be absolutely normal.
Yeah, that was my next question. How is it in Germany with the professional teams? How are they accepting or using those new computational, computer-aided techniques in athletic development and performance maintenance and so on?
So my experience is that it depends on the sport itself. And in Germany, the soccer teams are quite defensive. So a typical Premier League soccer trainer, yeah, knows what is best for the athlete, yeah. And if somebody is coming and doing some measurements and would like to give more detailed information to the trainer, you have to argue that this may be interesting for him or her. In other sports, for example, we were talking with the Olympic team of snowboard here in Germany, and they are absolutely open. They have said, oh, we can do everything to measure during, really, it was really amazing to have that discussion with them, because they were so open-minded to use these new techniques for their stuff. And I think it is depending a little bit on the people, on the trainers, on the medical doctors, but I think if you are now at the absolutely top leagues in Europe, in soccer, for example, or in other basketball or something, I think if you don't use these techniques in future, this will be, yeah, maybe not the best idea. I think it's because the others will use it, and it will become a normal technique. But the other thing is that we who are developing these kind of models, it's not necessary to not only develop the models which are able to calculate maybe the forces and so on, we are also responsible to present the results in a way that it's easily can be captured by the trainer and explained to the athlete. If we don't have that step as well, then you can have the best models ever, but it will not become part of training, because it must be fast and it must be completely clear, and then it can be transferred to the normal training sessions. But this is hard work, I must say.
Yeah, thank you for your insight.
Yeah, thank you very much.
Thank you, Thiago. Heiko, do you have any picture of the open lab to show to the students your facilities? Because I think that they got curious.
Okay, let's see, maybe.
Because, for example, when you were explaining to Adri your comparisons about motion and standard motion analysis systems and Xsense, and then you mentioned about the 7 force plates, then I just saw the face of Adri and said, oh God.
So this is the homepage of our open lab, yeah, and this is a view into the lab. Here you can see at the moment we have about 20 Qualisys high-speed cameras, which we can place here in the lab. And you can see here is a trampoline jumper. So the lab is really high. So it's 10 to 20 meters and this is as high as a normal gym is. And
excuse me, I don't know if it's just for me, but I'm not seeing anything.
Ah, excuse me.
Sorry.
You're right. What have I done wrong?
I think maybe.
So I do it again. Neue Freigabe. I didn't make the Freigabe. Okay, so this is desktop number 2. So now you can see a dog, hopefully. No, again, not.
No. Can you see the dog?
I can see.
Yes, I can see.
Oh, no. So now I skipped it. So I do a second Freigabe. So
now they can see.
Okay. So yeah, some pictures. This is so this is now the lab here. Maybe I can stop the movement. Here you can see the force plates. Yeah, so we can place the force plates in a row. So these are Kistler force plates, which the large Kistler force plates, which are 60 centimeters by 90 centimeters. So we can place them in a row, or 4 by 4 side by side to each other. This is the possibility how we can place the force plates here. And this is really nice to have that. So we are quite lucky. There are no many, I think this is no lab in Germany which do have this number of force plates. So there we have been lucky with a grant application. And we have the cameras here. We have an EMG system with 16 EMGs, wireless EMG. We have the possibility to measure the eye movement during the movement, and we have an EEG as well. So these are so this is the lab, treadmill, and you can place the camera outside. Here's again a nice picture. Maybe you can see the force plates here and the cameras. We have already also measured some dogs. It was really funny to do. We made some experiments with during crash. So we made some crash tests. In Münster, there's a crash test device where they are simulating crash tests, and we measured 2 people in the car with EMG and kinematics. So here you can see 4 cameras which are placed in the car, for example. Here we placed the cameras in a row to measure the car movement. Yeah. Excuse me, I don't have better pictures at the moment from the lab, but maybe this is an impression. Do I have some more? No. But maybe I can, if I'm here, because I really like that video. One second. Going back. Yeah, here, and then this one here, movement analysis. Yeah, I really like that video. It's Jens Natrup made it of my group a week ago or 2 weeks ago. Come on, come on. Why it's not working? Okay, I do it like that. Isn't that nice? This is made with an XN suit. I really like that one. Can you see the video, by the way?
Yes.
Okay. And but it's too slow. Excuse me. Yeah, but maybe you can have the possibility to watch that video on our homepage. No, it's too slow. I think it's the internet connection or something. I don't know. Yeah. Unfortunately, it's too slow. Yeah, that is some pictures of the lab.
So Heiko, well, I think there was a very students made a lot of questions to you, and I really enjoyed that.
Thank you very much for that.
And I think that we had a very nice opportunity for you to show what you and your group have been doing in the last years, all the things you have developed, and all the things that Myonardo can do. That's something that is quite amazing, and I feel very grateful to be honored to be there and to see you and your fellows developing all the things. So I think this was quite nice. And Heiko, I have 2 questions, because I think that during the presentation, maybe 2 things I don't think that students they very aware about. One thing is, why the option for the reservoir computing?
Okay. Okay, 1 second. Do I have a possibility to show it? Maybe this one. Yeah, okay. Take this from number 2. So hopefully you can. So this is this was a talk I was giving about, so typically you have a forward model and inverse model and comparator to describe the muscular activations. And we have developed, so this is a spinal segment, very nice paper, and you can see that there are a huge amount of neurons already in the spinal cord, and this is from a mice dissection. And so we thought that maybe this kind of theoretical yeah, what I can say that, and so typically you say that we have an intention to make a movement, that an inverse model which is generating motor control, then you have an afference copy to drive a forward model, and then based on this you can predict sensory feedback, and then you have the real feedback, you compare that, and then you can learn the movement. And we thought that where are these models in our body? So where is the inverse model in our body? Where is the forward model in our body? And the only thing that we have is a huge bag of recursive, connected and interacting neurons. This is the only thing that we have. We have muscles and bones and so on. And for the motor control part, we only have this highly connected neurons. And all what we are learning, what we are predicting or generating as activation patterns for the muscles must be generated out of a bag of neurons. That is how we say that. And therefore we said, maybe we can put all these models into one model. Come on. And we named it Inform, but it is always changing because we still have not the right word for it. So the idea is that we have an input, the intention of a movement. We have a neural network, which can be described with this quite simple formula. So this is a matrix. This is a Tambanks hyperbolicus, and this is n numbers. So it could be 1,000 neurons, or at the moment, Miriam de Graaf and Frederick Thies are doing some simulations with up to 3,000 neurons on a parallel computer in Münster, and because it's quite expensive, time consuming. And then we have the afference input from the muscles, for example, which is then activating the neurons here. And then you have the output, and the output is then the afference, so the activation of the muscles. And you can also have as an output the prediction how the afference will look like. And we made a simple simulation of an arm movement, calculated the movements and the activation which are necessary to do the movement. And we have, because in the Myonardo we also have the access to the length change and velocity and length and of all the muscles. So we have the some kind of an afferent information, and then we trained a neural network. So it's a reservoir computing network, and this is now the result. For example, if we have we performed the movement in the computer in different frequencies and with different range of motions, and this is a constant intention. So this means here, for example, the blue line here and the right line here means do a movement with a range of motion of 35 degrees and 1.5 hertz, and here's the change and so on. And then if we look in this area here, then you can see, for example, the 2 and 1A afferents of one muscle as an example only, because there have been several muscles which are included here into the neural network. And you can see the information. Here's the situation where you have the step, yeah, and then it's changing from this length change to this length change, for example. And you have the afference, so this is the activation time course for the muscle in this example, for example. And then after learning, you can see that the system can directly learn based on the intention. So from, let's say, 35 degrees to 25 degrees range of motion or something like this, that if you are changing the intention, the neural network with this recursive network are able to predict. So this is an overlay of the calculations. So what is the real afference of the model, and this is the prediction of the neural network. So this is quite similar, and also the prediction of the afferent signals is also learned and can be predicted from this neural network. So it seems that it is possible, while using this kind of reservoir networks, that the inverse model, the forward model, and the comparison can be performed not in different models which are somewhere in the body. We are able to perform this calculation within a highly complex reservoir network. Yeah, this is and at the moment we are not we, but the graph, for example, is changing the number of inhibitory and excitatory neurons in the neural network and the amount of connections between the neurons, and see how the learning process will be affected by this change of numbers. And Frederick Thies, for example, is using this kind of neural network to drive a prosthetic hand, a robotic hand, based on the measured EMGs, for example. And this is how we are trying to use this kind of reservoir computing networks to better explain, or maybe better understand how the spinal motor control system is functioning. This is in a very short way trying to explain what we are doing there. But if somebody of you have interest, or maybe would like to come in touch with us, or maybe Miriam, and Miriam and Frederick, by the way, are two PhD students who already have the grant to visit you in Sao Paulo. But unfortunately, they wanted to come last year, and still they're not allowed to come. But the grant was extended, so the money is still there. That's the good news. But we have to see whether maybe in October they will be able to visit or come to you to Sao Paulo, and then they would be very happy to have some collaborations with you.
Yeah, Heiko, I think that your explanation now shows us a very important thing that Myonardo has that the other ones don't have. This the forward computation, and because usually all the models, they are thinking in the feedback situation. And you do, and then you use information to do the next. But now you are trying to, you have information to predict what is going to happen, and you have some prediction, and then with this information you try to see if what is going on now is happening in the same way. That's something that is quite nice with your model, and that's why I ask you to show to students. And so I really appreciate that, and I hope the students enjoy your presentation. I don't know if students, I don't know if you have any other questions to Heiko.
There's one hand raised, I guess.
My question is about this last presentation. To understand the connection between these different regions, do you use transfer entropy or just correlation?
You mean, wait a second, please. You mean do you see that picture here now?
Okay.
Do you see that that slide here at the moment or not?
Yes, we can see.
Okay. So you mean that these different areas here, with your question?
Yes, to understand connection between them.
Okay. I go back to that. Oh, come on. So here I try to show that base. Maybe I increase the picture size a little bit for you. Not working. I don't know what. No. So this is the differential equation. It's a reservoir computing neural network. So the change of the activation of the neurons here, Q, is calculated with these matrices. So here is the blue area. So you have the afference signal. It means the xk means this is a vector of inputs of all the length and or proprioceptive information that we would like to input into the network. So this is a vector which is changing over time with the efferent signal. Yeah, and then we have a constant matrix. So this will be randomly generated at the beginning of the calculation. And so the efference input will then have an activation to, will activate this matrix, and the matrix is directly influencing the change of the neural activation of each of the n neurons that we have. Then, depending on this input, because of the plus sign, we are changing the activation status of each neuron. And for the next time step, we have a change Qn based on the blue area here. And this will then again influence the internal connections, or will be influenced by the internal connections M. And M is also we have two different ways to model it, but in a simple way, it's a force network. Then the M connections, so the connections between the neurons in that area here, is randomly chosen at the beginning, and we don't change that. Yeah, it's same for this I matrix. And then the only learning is present in this W area. So each neuron here in the M neuron, in the N network, has a connection to the output neurons here. So we have, let's say, the efferents could be maybe an alpha motor neuron of the biceps muscle or something like this. Yeah, and this neuron will be affected by all the other neurons of the M matrix. And during the learning process, we only change the weightings of this W network to all the other neurons here. So all the connections here are remaining the same. It's just, let's say, genetically determined, so in a first step, and only the learning process will take place in the projection to the output neurons. And this will be described here. So here you are changing the Q value. The Q value is then affected by this W, and the W value can be changed. This is also a matrix. And then the output is then the Y. Yeah, the efferents and the prediction, what else you would like to have as an output. Yeah, this is how we do model it. This is the force network, and we also have a full force network. Maybe you can search about these terms, or maybe you can ask me for the papers. These are papers which are not written by us, by others, and we are using this kind of network methods to use it in our model then at the end. Yeah. And the full force will have an extra network, and after learning, the extra network is turned off, and only the final network is used. And there are some issues that we have to address. There are some advantages and disadvantages. And in another paper, Myonardo de Graaf is at the moment trying to make a comparison between the two methods to describe it.
Okay. This internal connection don't depend of the complexity of test, I think, or not.
The internal connection, so we can change the number of connections in the reservoir. So, for example, at the moment, Myonardo de Graaf has developed a combined network, so such that we have one M network, which is only filled up with excitatory neurons, and one which is only filled up with inhibitory neurons. And so we can define how many connections we have in the two networks. So we can define whether each neuron is connected to all the others, or maybe by random connection, we only have, let's say, 10% of connections between the networks. And we can also define how many connections we have between the inhibitory and the excitatory neurons. And based on this, we can see how the learning process is advanced, or maybe it's disadvantaged by the differences of the connections, for example, and how strong the connections we can change as well. And these are huge amount of calculations that she did. And at the moment, we are hopefully very close. I don't know whether Miriam is here in the group. I'm very close for the publication of that paper.
Thank you so much.
Yeah, thank you.
Well, any other questions? No.
I like in the chat. I must say, I really would like to sign the last sentence here because I must say it's so inspiring to have a discussion, and it is so nice because each week on Friday we have a meeting with Louis, and it's so inspiring. And yeah, it's a great pleasure for me, Louis, that I think that we have now a friendship over
Yes.
10,000 kilometers already.
Yes, indeed, indeed. And you know, because Heiko and I, we have this is quite, for me, I would say that for me it's quite interesting, because before talking to you, I had also these ideas about forward computation and how important that would be to add to the normal biomechanical model. And so when I met you and you said you were doing that, oh God, you were doing the same thing I was thinking. That's nice. And well, and about the other method that we were connecting. So we had a lot of combinations about things that we think was very nice. And I think that I really enjoyed that. I really miss time in Münster, and I hope to have you soon here in Brazil as well.
Yeah, I really love to. Yeah.
Yeah.
I have to visit Sao Paulo.
Yeah. Okay, I think that we are good for now. Thank you so much, Heiko, for having us here. To be so open to the students and to give so many new information to them. I think that they're gonna sit down and think, oh God, how many different things in biomechanics Professor Heiko has shown to us. So thank you so much, Heiko. Thank you so much.
Thank you very much again. It was a pleasure.
And before ending the lecture, I will do I did it last time, and I think that it's quite nice. And Heiko, and I will ask the students to open their cameras, then Heiko can see all of you.
Hey, there are people behind this.
Yes, there are a lot of people, indeed.
So I hope that you will study long enough in Sao Paulo, such if I have the possibility to visit Sao Paulo, we can meet in reality and drink some nice stuff that
yes, yes, indeed.
Heard that you have interesting stuff to drink. Yeah.
Okay.
Yeah,
thank you, everyone. Thank you, Heiko. And
goodbye.
Goodbye.
Thank you.
Goodbye.
Bye bye.
Thank you, Heiko.
See you all tomorrow.
Thank you, Professor.
Bye bye, guys.
Very much.
Bye bye.
Okay, now I will stop recording.